Okay, let's continue with this question. Okay, as with the general application of Kirchhoff's rule, the first thing we will do is just write the currents. So let's call the current running through this wire I. The current running through this wire, let's call it I0. And the current running through that wire, I1. So now that labels all the currents we have. Now there's a junction over here. You see, here there's a junction. In this junction, the currents that are entering are I0 and I1. I0 and I1, they will be both carrying charges at that point. And I will be taking charges away from that point. So since there won't be any accumulation of charge anywhere, they have to be equal. So we have three unknowns. We don't know three. There are three currents that we don't know. So this is one equation that those three currents should satisfy. Equation 1. Now we need two more equations. And we will use the Kirchhoff's rules to write down those two equations. Kirchhoff's loop rule. Now let's take two loops. Which loop would you like to take? Just choose one. Let me give some labels to the points. A, B, C, D, E, F. Just choose one. You mean from A or from F? From A. Okay, let's start from A. Then to which? So from A you go to B and C. A to B and C. Then to the point D. Then the point E. Then the point F. Then A. So this is your loop. Somebody else. Somebody else? Choose one. You. B, C, D, E. Okay. B, C, D, E, and B. So this is the second loop. Now let's start from the first loop. Let's use the Kirchhoff's rules. VAA should be 0. Okay, what is the potential drop from the point A to the point B? 0. From the point B to the point C? 0 plus 0. From the point C to here, potential drop is plus V1. From that point to the point D, minus I1 times R, Y minus, we are going with the current, and the current always runs from the higher current to the lower potential across a resistor. Now from the point D to the point E, 0. Now, by the way, this is plus. This is 0. It's not minus because it's already a potential drop. We are summing the potential drops as we go along our loop. Now we are at the point E. From the point E to the point F, potential drop is 0. From the point F to the point A, what is the potential drop? I times small r. So V1 plus I1 r plus I times small r, this should be equal to 0. This is our equation 2. Now the third equation will be the blue loop. So let's see, the potential difference between the point C and the point C will be 0. Let's start from the point C. As we go from the point C, now let's also choose the direction of our loop. We are moving in this direction. From the point C to that point before after the battery, before the resistor, what is the potential drop? V1. What is the potential drop across that resistor? I1 times R. Between the point D and E, the potential drop? 0. Between this point and this point, what is the potential drop? The potential difference is I0R. Since we are going in the opposite direction of the current, it should be a minus drop, negative drop, so that's why we have a minus sign over there. And from this point to this point, what is the potential drop? Minus V0. So V1 plus I1R, this should be equal to V0 plus I0R. This is my third equation. So I had 3 unknowns. I don't know I0, I don't know I1, I don't know I. And now I have 3 equations to solve for them. This is my first equation. This is my second equation. And this is my third equation. Well, now the rest will be algebra. Let's do the algebra. So let me just use the first equation to write the second equation as V1 plus I1 R plus I0 plus I1 small r, this is equal to 0, or V1 plus I1 times capital R plus small r plus I0 times small r is equal to 0. Now, I'm more interested in I0 at the moment. So I want to know whether that battery provides the current or that the bad battery is being charged. So I want to know the sign of I0. If I0 is positive, then it is also providing a current to my car. But if I0 is negative, it will mean that I'm actually charging my V0. So let's see. If I want I0, let me use this equation over here to solve for I1. I will just move this to this side and divide by R. So I1 is V0 minus V1 plus I0R divided by R. Or I1 is equal to V0 minus V1 over R plus I0. This is my I1. I can just put that I1 over here. So V1 plus V0 minus V1 times capital R plus small r divided by R plus I0 times capital R plus twice R. This is equal to 0. What I did is I just took this I1, put it over here, and multiplied with small r plus capital R. This first term is this one. The second term just gives me I0 times this factor. I have another I0 times small r over here. I just sum them up. So I have I0 times capital R plus twice small r. And now I can solve for I0. I0 is equal to minus V1 over R minus V0 minus V1 times capital R plus small r over R. Oh, sorry. Let me write it this way. Multiplied with 1 over R plus twice R. So if you know the resistance, just put the numerical values over there. And if you know the potentials, then you will find I0. Well, let's see, V0 and V1. You see, V0 is smaller than V1. So V0 minus V1, this one is negative. Well, whether I0 will be positive or negative, well, it will depend. You see, if V0 minus V1 is large enough, so this combination will be negative, so I0 will be positive. But if V0 minus V1 is small enough, then this term will be negligible. So I0 turns out to be negative, which to me doesn't make any sense. Did we make some mistake somewhere? No. You see, I1 is running in this direction, I2 is running in this direction. So this equation makes sense. Oh, sorry, let's see. So let's just look at this again. So we go from C. This is the potential drop. This is the potential drop. Yeah, okay, this is correct. This is the potential drop. Now, okay, this makes sense. So let's see if we wrote this equation correct. The red one, we started with V1, I1R, then capital I times small r. This should be equal to 0. The equations are correct. Let's see about our solutions. That is fine. So from this one, so here I1, okay, that is fine. Then what we did from this one, we solve for I1. I1 is V0 minus V1 plus I0 times R over capital R. This is correct. Then I put it over there. This is the equation we have, and okay, fine. This is the last equation I have. Everything seems to be fine.
What should be the sign of I0?
Well, what I expected, to be honest, you see, if V0 and V1 are equal, they are both good enough batteries. And let's say if small r is infinitely huge, so that no current runs through that. Well, both batteries are equally strong, so there shouldn't be any current running through the system. If small r is infinitely large and V0 and V1 are equal. If V0 and V1 are equal, this term is 0. We have I0 is V1 over this ratio. If small r is infinitely large, there is no current running through the system. At least that makes sense. Let's say if V0 and V1 are equal, and R is not infinitely large, this tells me that I0 is negative. You see, if V0 and V1 are equal, this term just is 0. None of the resistances are infinitely large. So this tells me that I0 should have a negative current. Oh, that makes sense. So probably that was what you were mentioning. Okay, that also makes sense. If V0 and V1 are equal, we will get a current running through this circuit, and there will be a current running by pushed by this battery, and the current pushed by this battery. They will be both in opposite direction to these ones. So this is the plus, this is the minus. So the current here should be running in that direction. The current should be running in that direction. My interpretation, my first interpretation was wrong. If I0 is positive, that you see, usually this battery tries to push current in this direction. This is the plus, this is the minus terminal. So the normal way of running the current is in that direction. That tells me that I0 should be negative. If I0 is positive, then I'm charging this battery. So now everything now makes sense, at least to me. Sure, yes. You see, this is an example where I was wrong in judging the direction of the currents initially. But if I did everything consistently, the result already told me what should be the correct direction of the, what will be the actual direction of the current. I found a negative current, which told me that the current is actually running in this sense. So it doesn't really make any difference how you choose the initial directions of your currents. That is just the definition of positive current and negative current. Any other questions? Okay, so let's look at an example from the book. Problem 36. Well, it is in fact similar to our previous, our jump starting a car example. So we have one battery. There's a resistance over here, another resistor, another battery here, another resistor. Now let's just use one of them. And then another resistor, and still a fourth battery. So let's say this is R1, R2, R3, R4, R5, R6. So this is I3, this is I2, and this is I1. Well, in the book there are also the numerical values of the batteries and the resistances. But let's just write down the physics is up to writing down the Kirchhoff's rules. So what do the Kirchhoff's rules tell us about these three currents, I1, I2, and I3? We have three unknowns, and hence we should have three equations. Let's start with the junction rule. Here we have a junction. The current entering this junction is I3 and I2, and I1 is leaving the junction. So I2 plus I3 should be equal to I1. So whatever charge arrives at this point, it should also leave. So I2 plus I3 is just I1. Now we have two more equations, and those we will write using the loop rule. let's say this is one of my loops. And let's just say that the other loop is this one. You can just choose whichever loops you like. Let's start with the red one. Let me start from this point. What is the potential drop? Or let's just say that they all have the same EMF. V, or V1, V2, V3. Now, what is the potential drop as I go from this point to this point? Minus V1. Okay, from this point to this point, I2 is in this direction. It's I1R1 plus I2R1. Positive or negative? That is the direction of the flow of the current. That is the positive direction, so that's plus. Okay, from this point to this point, I2R2. From this point to this point, potential drop is minus V2. And from this point to this point, this is I2, R4. I'm moving in the direction of the current, so it's positive. And from this point to this point, what is the potential drop? The current is, no, this is I1. Sorry, this is I1, not I2. So these are all I1. This is I2. So here, I1 R3. This should be 0. So this is my second equation. Now we can write the third equation as we go around this blue loop. So let's start from this point. From this point to this point, what is the potential drop? The current is I2, resistance is R4. I'm running in the opposite sense of the positive current, so there is a minus I2 times R4. As I go from this point to this point, what is the potential drop? The current is I3, resistance is R5. So I'm going in the same direction of the current, the positive current. So it's plus I3 times R5. As I go from this point to this point, what is the potential drop? Minus V3. Now, as I go from this point to this point, what is the potential drop? I3 times R6. And I'm back to my initial point. So I have three unknowns. I don't know I1, I don't know I2, I don't know I3. And now I have three equations to solve.
Why we didn't write it?
Well, because I forgot. As we go from this point to that point, what is the potential drop? Minus V2. No, plus V2. Now I have three equations, three correct equations, hopefully, for three unknowns. This one, well, let's see, that corresponds to, it was this one. This is I1 R3, this one. Oh, yeah, this is R3. Now, what is the potential difference that you would measure between the terminals of, let's say, this battery? You have your circuit, you take your device to measure potential differences, and you connect it to the terminals of the battery. Will you measure V2? So what will you measure? So let's see. Basically this R is nothing but the internal resistance. So when you connect your measuring device to the terminals of the battery, you are measuring the potential difference between these 2 points. So let's see. What is the potential drop as you go from here to here? Minus V2. What is the potential drop as you go from here to here? I2 times R4, plus or minus? This is the terminal voltage. You won't measure V2, but you will measure a smaller potential difference.
Şimdi yukarıda belki o şeyden çıkarsak mesela 0 eşit olmasından o yine belki olmuyor.
Which one?
Yani biz burada tam olarak neyi ölçüyoruz?
Here. Here. Well, here, I mean, this is your battery. This is one terminal. This is the outside terminal. You measure the potential difference between the two. But the internal resistance is between these 2 points. So what you will be measuring is this potential difference, not this one. V2 is the EMF of the battery. R4 is the internal resistance of the battery. Since there is a current running through your battery, the potential difference you will measure between the terminals will not be the EMF of the battery. It will be different it will differ from the EMF by this much. No, I didn't choose a loop. I just chose 2 points. And I just calculated the potential difference between these 2 points. This is not 0. It's just smaller than the EMF of the battery. Any questions on this one? Let's look at question 49. We have a battery. Then it's connected to a switch. Beyond the switch, there is a resistor. And there is another resistor. And parallel to that resistor, there is a resistor with a capacitor. And the currents are given as this is I1, this is I2, and this is I3. This is plus Q, this is minus Q, and all the resistors are equal. This is the circuit we have. Now let's see what it asks. At t equal to 0, the capacitor is not charged. It's neutral. And then we close the switch. We know that the capacitor will slowly charge. Now let's see. What is the current at t is equal to 0? At t equal to 0. Why should it be 0? You see, we have 3 currents anyway. I mean, at most one of them would probably be 0, but not all of them. Well, let's see. At t equal to 0, what is the charge? There's no charge here. What is the potential difference across it? It is the potential difference is 0. So at t equals to 0, the circuit is essentially this one. Well, the capacitor doesn't affect the current, because since it cannot create any potential difference. But this circuit, you see this, let's say this is EMF is E. This is R, this is R, this is R. But this circuit is the same as this circuit. Well, you see, these two, what is the equivalent resistance of these two resistors in parallel? Plus another R in series, 3R/2. So I1, what is I1? The current running through this wire, or this wire, or this wire, is E over 3R/2. And what about this? This is our I3. This is I2. What about I2 and I3? Well, the resistances are equal. So this I1 basically splits into 2. And the I2 and I3 are equal, and they are half of I1. This is at t equal to 0. When the capacitor is not charged, when it's neutral, since it cannot create any potential difference, it is as if it is not there. This is what happens at t equal to 0. Now let's look at what happens at t goes to infinity. So we wait for a long time. I3 is non-zero, so it will start charging the capacitor. Eventually, the capacitor will be fully charged. Fully charged meaning that it will not allow any more charge to be deposited in the capacitor. So what will be I3? Now I3 will be 0. Since it doesn't allow any more charge to be deposited on it, well, I3 will keep on depositing charges, so I3 should be 0. Well, since I3 is 0, there is no current running through this wire, so it practically doesn't exist for the purpose of this circuit. So we have our simpler circuit is this one now. R and R. What is the current? This is I1. Well, I3 is 0. If I3 is 0, I1 and I2, they are equal. This is I1. This is I2. I1 is equal to I2, which is equal to 2R. Now, at t equal to infinity, what is the charge of the capacitor? So let me just redraw the full circuit here. So this is the current I epsilon over 2R. The current here is also epsilon over 2R. What is the potential difference across the capacitor? Why? That's the correct answer, but why? Well, let's see. What is the current running through this resistor? 0. At t is equal to infinity. There is no current running through the capacitor, so there is no current running through this resistor. So what is the potential change across the resistor? 0, because there is no current running through it. So the potential difference between these 2 points is just the potential difference across the capacitor, because the resistor doesn't change the potential. Well, the potential difference between these 2 points is the same as the potential difference between those 2 points. So the potential difference between these 2 points, or across the capacitor, is just epsilon over 2R. This is the current running through this resistor, and its resistance is R, epsilon over 2. This is the potential across the capacitor. What is the charge of the capacitor? C times V. C times epsilon over 2. So when you have capacitors in the circuit, it's kind of easy to analyze the circuit when initially when the capacitor is neutral, because it just behaves as if it doesn't exist. And it's also easy when the capacitor is fully charged, because what we mean by fully charged is that it no longer allows any current to run through it. So the current is 0, and the capacitor is as if it's open circuit. For any time in between, the capacitor is not yet fully charged, but it's also not empty, well, then we need to use the Kirchhoff's rules. Let's write the Kirchhoff's equations for this circuit. So this is our circuit. Let's start with the junction rule. Now, there is a junction over there. What are the currents that are carrying charges to that junction? I1. What are the currents taking away the charges from that junction? I2 and I3. Okay, this is one equation we have. How many unknowns do we have, by the way, in this question? 4. We don't know the current, but we also don't know the charge of the capacitor. So we need 4 equations. This is one of them. Now let's write the relation between the currents and dq by dt. So dq by dt would be the current, total current entering my capacitor. What are the currents entering my capacitor, depositing charge on my capacitor? I3. So dq by dt is I3. This is one additional equation I have compared to the other examples we had discussed. Now I have the loops. Let's say this is one loop, This is the other loop. Now let's start with the blue one. What is the potential drop as I go from this point to that point? The potential drop is minus epsilon. Now this circuit is now closed. Well, there is no potential drop. What is the potential drop between this point and this point as I cross that resistor? I1 times R. Now from this point to this point, as I cross this resistor, what is the potential drop? I2 times R. Sorry, this is I plus I1 times R plus I2 times R. And now I go, well, I'm back. I don't cross any resistors, any potential differences, so this should be 0. This is one equation we have. And finally, let's see, let's start from this point. What is the potential drop as I cross this resistor? I3 times R. What is the potential drop as I go from this point, as I cross this capacitor? Q over C, and I'm going from higher potential to lower potential, and it's actually a drop. And then I'm now crossing this resistor. What is the potential drop as I cross this resistor? Minus I2 times R. This is equal to 0. So I have 4 unknowns. I have 4 equations. Any questions on how we write these Kirchhoff's rules? This one. It's just to signal that that switch is closed. This one. Now, the most confusing part in using the Kirchhoff's rules will be to determine the signs. Most mistakes are from the signs, whether to put a positive sign or a negative sign. And, well, just for completeness, I forgot to mention one name. You see, we solved these circuits. And this was this is when it is discharging. The charge as a function of time was determined by that exponential. And when we were charging the capacitor, the charge was given with such an expression. Here we have exactly the same exponential, in fact. And if you look at the current as a function of time, here we have exactly the same current, exactly the same exponential appearing all the time, e to the power minus t over RC. This RC is sometimes denoted as tau. It is called the time constant. It essentially determines how fast you can charge or discharge your capacitor. You see, when you are charging the capacitor, if the time t is much smaller than your time constant, this is very small, then this exponential is almost 1. So your charge is almost 0. So this RC basically determines the time it takes for you to charge your capacitor to a significant charge. For times much smaller than RC, there's practically no charge in your capacitor. For times much larger than this time constant, your capacitor is practically full if you are charging. If you are discharging, if T is much smaller than this RC, your time constant, there is practically no change in the charge. If T is much larger than your time constant, then practically there is no charge left in your capacitor. By the way, what's the unit of RC? Seconds. It's actually a time. Any questions? Any questions about anything in electricity? Because next week we will be starting magnetism. So see you tomorrow. See you on Monday.